All right, so the last time we spoke, the notes that we went over, they were for work. And work was defined as the transfer of energy by mechanical means in order to perform some task, okay? So that's what work is. So today we're looking at what is energy. So energy is the ability of a system to produce a change in itself or the environment. You have the ability to produce a change in itself or the environment, all right? So when you take this energy and it is being transformed in order to perform a task, what you're doing is work, all right? So when work is done, this is for the work energy theorem, and you need to leave some room for an equation. So when work is done, it results in a change in the system's energy. All right, when work is done, it results in a change in the system's energy. So basically, it's kind of like what you put into it is what you're going to get out of it. Does everyone understand that? All right, so I have to use energy in order to perform work, to perform a task. The more energy you put into it, the more work you're going to get out of it. All right, does everyone understand that? So what happens is, as far as how they're related, your work, the work that is done, or the work that is performed, as far as that amount of energy, it is going to be equal to the change in your energy. Okay, so E stands for energy. W is for work. And I'll put this in parentheses. So work equals change in energy. Okay, where energy is E. Symbol for energy is E. All right. Can you name different types of energy? What are some different types of energy? Different types of energy. Go ahead and put it in the chat.
Potential.
Potential energy is one. What else? What other energies do you know about? Kinetic energy, good. There's thermal energy, okay? So there's chemical energy. Yes, heat is thermal energy, good. All right, so what happens is this equation, this is very generic. It says work equals a change in energy, all right? So it doesn't have to be one specific type of energy. We'll be talking about one type of energy today. Specifically, it's going to be kinetic energy, all right? And how the change in kinetic energy results in work, okay? So how these are going to impact each other. Talking about kinetic energy, but again, this equation is really general. So as far as work is equal to a change in energy, it could be a change in kinetic energy, it could be a change in Potential energy could be the change in thermal energy, all right? Wherever that energy is being transformed, whatever type of energy it is being transformed to perform a task, okay? Work is going to be done. So you can look at it. It does not, again, it's not just necessarily one type of energy. You can have multiple energies that are happening here, all right, to have work done. All right, but specifically what we're going to be looking at today is your kinetic energy. So when we say it's a change in energy, remember that change means you have some kind of final minus initial. When we talked about change in velocity, we had a final velocity minus an initial velocity. If we talked about change in time, you're talking about the final time minus the initial time. What else? We talked about the change, your displacement is a change in position, all right? So that was your final position minus your initial position. So anytime you're talking about a change, you're talking about some kind of difference. So as far as this, another way to write this is that your work equals your change in E is the same as writing E final minus E initial, okay? Final energy minus your initial energy. What you started with, what you end up with, all right, to produce the work. All right, so the equation for kinetic energy, since that's the one that we are talking about today, first off, what is kinetic energy? It's energy associated with what? What do you have to be doing in order to have kinetic energy?
Motion.
Motion, you have to be moving. So this is energy associated, thank you, with motion. There has to be some type of displacement happening, movement. So the equation for kinetic energy is kinetic energy equals 1/2 times your mass times your velocity squared. Okay, so if I was to break that down just looking at the units to figure out the SI units of kinetic energy, work is measured in joules. All your energies are also measured in joules. Doesn't matter what type you're talking about, potential, kinetic, thermal energy, chemical energy, they're all going to be measured in joules. So we have joules, it's a unit of measurement. Symbol is J. Okay, so if I look at this, I'm going to break this down. It was 1/2 mass times velocity squared. So as far as your mass, the units of mass are kilograms. I'm just showing you how we get joules. And the units of velocity, what is velocity measured in? What units? Y'all can put it in the chat. What are the units of measurement for velocity?
Meters per second squared.
Meters per second. Meters per second squared is for acceleration. It is meters per second, but then what happens is we're going to square the whole thing. So what we end up with is kilograms times meters squared over seconds squared. Okay, so if you remember for your force is kilograms times meters per second squared. So if I got rid of one of these, that would be kilograms times meters per second squared is a Newton, and then you'd be left with a meter. So if you recall from the last notes, a Newton meter is the same as a joule, all right? So that's where that unit of measurement comes from. Okay, so kinetic energy is 1/2 mass times velocity squared. For the work equation, we said that it is looking at a change in energy. So that means there has to be a final minus an initial. So that's what we would be looking at here as far as the relationship between the work and kinetic energy, is that work would be equal to a change in the kinetic energy. Okay? So I'm going to put that equation right here. So work, specifically the KE equation, is going to be work equals your change in kinetic energy. Okay? Which means it equals KE final minus KE initial. Okay, so you're going to have your kinetic energy equation is 1/2 mv squared final, whatever that is, the final velocity, minus 1/2 mv squared, your initial. Okay, we're going to look at a couple of problems for that. Okay, so let's take a look at number 1. Remember that, again, you're supposed to show your list, basic equation, solution, and a box your answer with the units. So for this one, we have, it says a 6 kilogram cat. Runs after a mouse at 10 meters per second. What is the cat's kinetic energy? All right, so that's going to be your list. The equation for kinetic energy is 1/2 mv squared. Okay, so once you have that, you have your mass and you have your velocity, so you just plug in your numbers. Make sure to square the velocity. So it's 1/2 times 6 kilograms times 10 meters per second squared. 10 meters per second squared, that's 100, times 6, 600, divided by 2 gives me 300 joules. So this is what your work should look like in your assignment. Are there any questions in this one? Questions for this problem? All right, so number 2 says, suppose the above cat accelerated to a speed of 12 meters per second. So started at 10 meters per second, ends up at 12 meters per second while chasing the mouse. How much work was done on the cat to produce this change in speed? Okay, so we know that the mass, again, is 6 kilograms. Says the cat accelerated to a speed of 12 meters per second. What is this? We're looking for work, and we know that work is a change in energy. Specifically, the energy that we're looking at, we're focusing on today, is your kinetic energy. So work equals a change in kinetic energy. Okay, so that means we are going to need KE final minus KE initial. 1/2 mv final, so we need a final velocity, minus 1/2 mv squared initial, we need an initial velocity. So I have 6 kilogram cat, we need a final velocity, and we need an initial velocity to figure out work. So what is the final velocity of this cat? Okay, thank you. It's 12 meters per second. What was the initial velocity? (10 meters per second). Right. Breaking this equation down, KE final is 1/2 mv final squared minus your KE initial, which is 1/2 mv initial squared. We actually already solved for this part because the initial velocity is 10. That's what this is up here. So we don't have to write this out again. We could just fill in that number, 300 joules, when we get down to this part. What we need to do is complete this first part. So we have 1/2 times the mass, 6 kilograms, times the final velocity of 12 meters per second squared, minus your initial kinetic energy, which is 300 joules. Okay, so go ahead and calculate that. Tell me what you get. What do you get for this part first? For the KE final, what is it? (12 squared times 6 divided by 2 gives you what? All right, it is 432 joules for this, minus your 300. It's going to give you a value of 132 joules, which is your work. Your work is your change in your kinetic energy for this example. All right, power. Power is the rate at which your energy, whatever energy you're talking about, whatever type of energy you are talking about, the rate at which energy is transformed, the rate at which you are taking this energy and using it to perform work. All right? So just as your velocity is the rate at which your position is changing, all right? So that is for your velocity, that means you taking your position divided by your time, all right, to figure out the rate at which the position is changing. To figure out the rate at which energy is changing, then, what you're doing is you are taking your work or your energy, that change in energy, and you're dividing it by time. So power equation is power equals the change in energy divided by time. Or, remember that your change in energy is work. So if you know what your work is, you don't need to break it down into delta E. So this is work divided by time. Now, what would be the SI unit of power? What's the standard unit of measurement for power? What is work measured in? What is work measured in? Joules. And what is time measured in? What do we measure time in? Standard unit. seconds. So it's joules per second. This is also known as the watt. Watt is joules per second. Okay, the symbol for this is a capital W. All right, let's look at the practice problem. It says an electric motor lifts an elevator 9 meters. What is that? What information is that? Goes up 9 meters. For my list, what do I label that as? 9 meters is?
Displacement.
Good, displacement. In 15 seconds, that was your time. By exerting an upward force of 1.2 times 10 to the 4th newtons. What power does the motor produce? So we're looking for power. But be careful because they want the answer in kilowatts. Kilowatts, not watts, all right? And when we have joules per second, if that's what we get, then we know that's watts. So you will get your answer in watts. You need to make sure to convert to kilowatts, which is the same as going from meters to kilometers. Okay, so when we get watts, we need to convert it to kilowatts. Okay, so power equation. Look at the list that we have here. So do you think we need the delta E over T, or do we need the W over T to solve for this? Look at your list, look at what you have to work with. Do we want to use delta E over T, that change in energy over T, or do we just want to use work divided by time?
Work divided by time.
Good, it'll be work divided by time. Because looking at this, I have a force, vertical force that's being used, and it's moving at 9 meters vertically. So we have enough. Remember, your work is your force times your displacement. So we can solve for that and divide it by the time we have. So 1.2 times 10 to the 4th newtons times a displacement of 9 meters divided by 15 seconds. Comes out to 7,200 Newton meter divided by time, by seconds, is going to give you watts. So this is 7,200 watts. Okay, but that's not what we need. We need kilowatts. So how do I change watts to kilowatts? Again, think about it, going from meters to kilometers. We're going from a small unit to a much larger unit. What would I do to go from meters to kilometers?
Divide by 1,000.
You would divide by 1,000. Good. So the same thing here, going from watts to kilowatts, you're going to divide by 1,000, which means your answer will be 7.2 kilowatts.